Alright, cool. It's recording, right? Okay, yeah, it's recording. Okay, so here we're going to be practicing mock interview for Leetcode problem 2275, largest combination with bitwise and greater than 0. So the problem description reads as follows: the bitwise and of an array nums is the bitwise and of all integers in nums. And for example, for nums 1, 5, 3, bitwise and of 1 and 5 and 3 is 1, and for 7 the bitwise and is obviously self. So that's the definition of a bitwise and of an array, just taking the bitwise and over all the elements in it. So you have an array of positive integers candidates. Compute the bitwise and for all possible combinations of elements in the candidates array, and return the size of the largest combination of candidates with a bitwise and greater than 0. Okay, so I think the first thing to note is that we have like an array of candidates, right? And we have to return the largest combination of candidates with bitwise and greater than 0. So I'm just going to ignore the part where it says compute the bitwise and of all possible combinations. We don't actually have to do that. There's probably a more efficient way to do that than to just generate, say, all possible combinations. And obviously, to say generate all possible combinations of elements in the candidates array, we can adopt, say, like a brute force approach, which is to simply just generate all possible subsets, then check the bitwise and of each of them, right? And that's obviously like the most straightforward way of checking whether or not, say, like, you can get a bitwise and greater than 0 if we just, obviously look at every single possible subset. And since like the number of subsets is 2 to the n, and to check, say, like the bitwise and is all of n, you obviously have to take the bitwise and of every element in the array, and the biggest, say, like possible subset size is n, so worst case complexity is, say, exponential times linear. So that's one approach. And yeah, so we can probably do better than this. And first of all, when it says that all possible combinations, I'm curious whether or not, say, we can have duplicate elements in the array. So yeah, in this case, candidates 8, 8, output 2, the largest combination of 8, 8 has bitwise and of. Okay, yeah, sounds good. So duplicates are allowed, right? And we have to pick the biggest size subset such that the bitwise and of the array, the numbers, is greater than 0. So first of all, what makes an array have a bitwise and of greater than 0? Let's see. So to have bitwise and we say have, say, some array of elements, right? So if we say just consider, say, like, very small example, if we just consider, say, like 8-bit numbers, right? We have, say, like A1, A2, A3, A4, A5, A6, A7, A8, and say B1, B2, B3, B4, B5, B6, B7, B8, etc. And let's just say that this, like, say, continues on up until, say, like, some arbitrary elements, such as, well, let's just call this Z1, Z2, Z3, Z4, Z5, Z6, Z7, Z8, right? So then the bitwise and of all of these is going to be, say, like A1 and A2 and B1 and C1 and D1, etc. and etc. Right? So what we're just going to immediately know is that the resulting number is going to, say, like, be the bitwise and over, say, all of the columns, right? Where each bit is either 0 or 1. So for it to be 0, this means that the bitwise and of this has to be 0, 0, 0, 0, 0, 0, 0 for every single bit. That's what it means for, say, like the bitwise end of this array to be equal to 0. And for that to happen, we need at least a 0 somewhere in each column, right? A 0 could be here, here, or like say like here, here, here. All that matters is that every column of bits here, there's at least 1 0 in some row, right? So for it to have a bitwise AND of greater than 0, that means that there exists some column of bits such that every single bit, say like, if we say like focus on the ith column, every bit in the ith bit for like every number in your picked array has to be a 1. And this could be any one of these. So then this automatically tells us that, first of all, for some number I, every ith bit of your numbers have to be a 1 for the bitwise and to be greater than 0. And that tells us like that is what satisfies it, right? So then it means that if we consider, say, like the pivot column, or say like the ith bit for which we're considering, to maximize this choice, we just have to pick all numbers that, say, have like a 1 in the ith bit, right? And that would be, say, like greedily maximizing our choice, because, well, like if you can take all the numbers in it such that, say, for the ith bit, you take all the numbers that have a 1 in the ith bit, you're trying to maximize the size, so you take every single element that has a 1 in that bit, right? And if we do that for every single possible position, we have to consider all possible, say, sizes in which, okay, let's like at least have, because like if we have, say, like the optimal subset, right? The optimal subset must have some column that has all 1s, right? And therefore, if we iterate over every possible column and check what's the maximum size that can be achieved by focusing on that column having all 1s, then we'll have reached our solution that way. So then our algorithm comes as follows. So iterate from, say, like the 1 to 32th bit, and for each position, iterate over all elements of the array, right? Or say like, yeah, iterate over every element in the array, and for each element, increment by 1 for the ith, say, like subset, if, say, like array of I has a 1 in the ith bit, right? And then we take the maximum sized subset by keeping track of, say, like the size of this subset in another array, and we just return the maximum after iterating all of this. And the time complexity of this is O of 32 times n, or O of n. So I think that overall does it. I don't think I'm missing anything, so I'm going to try to code it up. So first of all, candidates is up to 10 to the 7th, so that honestly should be like, say, like 25 bits or so at most. But I'm just going to quickly check. 2 to 25 is 1, 2, 3, 4, 5, 6, 7. Actually, it's more like 24 bits. So, okay, let's say counts is equal to 0, 4, 24. Okay. Or actually 25. I guess. Okay, so just to be on the safe. So for every number in our candidates, let's also keep track of, say, like our maximum subset size to be 0. Then let's say like iterate over, say, like the bits. So for I 25 if x right shifted I and 1 is equal to a 1. Well, actually, we don't need the equals. We can just check, say, like the truth value of this. So if it is a 1, it will return true. Then we have counts of I plus equals to 1. Max size. Actually, we don't need to compare. I think we can just do it with, like, say, a size 25 loop at the end. That should be it. So then we iterate over size 25. Equals to x, and we return x. We return max size. And just to say, check over this, we first initialize this. Size equal to 0 for every number in candidates. I spell this, iterate over the 25 bits. So then if the ith bit is a 1, we obviously increment that as a potential subset size. And then for every return max size. Awesome. And so far that looks good. Oops, and look at that. It is good. Okay, so currently memory is a little sketchy. Why is memory a little sketchy? Who knows? Honestly, I can't think of a way to like optimize this more. That's probably good enough for now, to be honest. Can't think of a way to optimize this. Like, you do have to keep track of, say, like, all these subset sizes, so this is unavoidable. You obviously have to check every number in the array because it could belong to, say, some subset. And if you don't check every element, then you could always, say, generate some case where it fails. So yeah, looks good to me. I mean, it's accepted, and yeah. Oh well.